good afternoon to all the participants present here. I am really honored to welcome Dr. Lalit Kumar Singh and to read his introduction. So, Dr. Lalit Kumar Singh received his PhD degree from Indian Institute of Technology. Now it was earlier known as the Banaras Hindu University. He is currently a scientist in NPCIL, BARC, Department of Atomic Energy, Government of India since 20 years, and has distinction of working on pressurized heavy water reactors and light water reactors. He has an illustrious career and succeeded in several critical jobs assigned to him in his illustrious career, though each of them was challenging. His assignments over the years range from design, development, testing, IV&V related researches, and site validation of the safety critical computer-based systems of Indian nuclear power plants. He has published several research papers in journals of high impact factors like the IEEE transactions, IEEE computer ACM, etc. He has been invited for chief guest keynote speeches, session chairs, and talks in many international conferences, short term courses, workshops, and faculty development programs from many IITs, NITs, and other institutes of national importance. And he is also a recipient of many awards like publication awards, group achievements, etc. And he is a reviewer of several SCI indexed journals of high impact factor. And also, he is a life member of Indian Nuclear Society. He is a founder member of and industrial coordinator of the proposed Center of Dependability at IIT BHU. He is in the panel of Faculty Assessment Committee of the Department of CSE IIT Roorkee to assess their research profile and give recommendations. He is a member of editorial board of many reputed journals and guest lead editor of many special issues. He is supervising many PhD students of different IITs, NITs, and is PhD thesis examiner of IITs, NITs, and other reputed institutes. And also, he is an expert member of Industrial Policy Formation of IIT Ropar and of many autonomous institutes and member of the advisory board of many institutes and universities. And he is a reviewer and project collaborator of research proposals of Board of Research in Nuclear Sciences, BRNS. He is also a faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France, etc. for importing nucleus reactors that are based on new technologies. His research interests are in the areas of reliability, safety, security of safety critical computer-based systems. And so far, he has completed 33 projects of Department of Atomic Energy, Government of India. There are many more achievements to provide an introduction about Dr. Lalit Kumar Singh, sir. So I welcome you, sir, for your session.
Thank you, madam, for introduction and for providing me this opportunity to share some of the experience to all the participants. And so, just to start with, let me share my slides. So, are my slides visible?
Yes, sir.
And just let me check whether these are changing or not. Now the slides are changing?
Yes, sir, they are changing.
Yes, sir.
Okay, thank you. Thanks. Yeah, so I'll be talking on reliability analysis of IoT communication protocol for safety critical systems. So before going to the main contents of the topic, first let me introduce about the importance of this topic so that a motivation can be drawn and the audience can take the interest on the entire session. So I'll be focusing on safety critical systems And these systems are those systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And there are several domains where we make the use of safety critical systems that include like automobiles, medical domain, defense domain, nuclear energy, aerospace, railways, a lot of other domains. And these applications are known as the critical infrastructure of the country, and hence the computer-based systems, which basically controls the working of these applications, are very important and are safety critical in nature. And if they fail, it can lead to the severe consequences. And hence, it is very much essential to perform the reliability analysis for such systems. Now, coming to the reliability, let us see what does reliability mean. So, if we talk about the definition of reliability, it's so this definition, each and every word of this definition has very important meaning, which is necessary for us to understand. So when I say like reliability of the system is a probability of failure-free operation, so probability in the sense we know in the mathematical terms its value ranges from 0 to 1. So one thing we can draw from here, if we talk about the quantification of the reliability, we can have the values from that can range from 0 to 1. And 0 means the least reliable and 1 means the highest reliability. So then in the definition, I said up to the given period of time. Now anything is not reliable for infinite period of time. Even if you can recall your childhood days, you may be having some friends whom you may be thinking they are going to become your best friend throughout your life. But as and when the situation gets changes, the dynamics gets changes, and the demand gets changes, the interest gets changes, and because of the current circumstances, you start making new friends, and that probably may be replacing the older friends even. So what I mean to say here, even the human is not reliable for infinite period of time. So when you talk about the reliability of any particular thing, you have to tell up to what period of time you are talking about. And that time is known as the target time. So the reliability is always a function of time. Now, whether now you may be thinking like how it happens in the case of software. Yes, it can happen in the case of software as well, because any software runs on the electronics platform or hardware platform, and hardware becomes obsolete very fast, and you may have to change the hardware platform, and accordingly you will have to change the software APIs or to transform it to be workable on the new platform, or probably in the software itself you may be trying to add on new features, and so it also keeps on changing. So now the next, coming back to the definition, I said under certain environmental condition, reliability of any system is the probability of the failure-free operation of the system up to given period of time and under certain environmental condition. Now this environmental condition plays a very important role, because if one thing or any one component or even a human may be high reliable at one environmental conditions or may be less reliable in other environmental conditions. So what I mean to say, for example, you go and purchase a refrigerator from a vendor, and suppose he gives a warranty period of 1 year, and when you come back with the refrigerator and suppose you throw it from the 14-story building, it will collapse. Then you cannot go back to the vendor and say, look, you have given the warranty period of 1 year, so I want the replacement of this refrigerator back. What he will say? He will say, look, you have not met the operating conditions under which this product was supposed to be operated, and hence the warranty has been voided. So here, so what I mean to say is, when I talk about the reliability, you will have to consider the environmental conditions or the runtime conditions under which the product is currently under operation. So I'll be talking on a reliability analysis of IoT communication protocol. You know, like in the IoT, there are the different processing modes, and those may be having some heterogeneous functions, and probably one node is passing some data to the other processing node, which is processing that particular input to reach or to decide something. Probably it is transforming that information into some more meaningful data and more meaningful information, and that information is again flowing into different processing nodes for the to accomplish the overall objective of the function of the system. So what I mean to say is, you do have a different processing modes, and probably those are remotely connected as well. So definitely there is some communication needs, and communication, once the things are connected through some communication means, definitely it is a trait, and you'll have to, like, compute the reliability of that communication module as well. So I'll be specifically dealing with the communication protocol, and I'll be demonstrating how we can perform the reliability analysis for the communication protocol of this IoT for safety critical systems. So let us go through today's agenda quickly. So first, we will discuss the introduction to reliability and background. Although we have discussed a lot, but we can see like how what is the mathematical representation of the reliability, and then we will discuss about the battery nets and modeling of the system. Now, battery net, it is a mathematical formalism or mathematical model that was introduced by C.A. Patrick, who was a German PhD scholar in 1960s, and he introduced this model to capture the stochastic behavior of a system, or to model the stochastic processes. So if I categorize the processes, I can do it into two types. The first one is the deterministic process. The other one is the probabilistic or stochastic process. Now let us try to understand what the type of processes we mean. So deterministic processes are those processes the outcome of which can be 100% guaranteed. For example, suppose I do have a pen in my hand and I drop a pen. then I can 100% guarantee it is going to fall down on the earth. Why? Because of the gravitational force that is acting on that planet. So, what I mean to say is here the outcome can be 100% guaranteed, and hence this is deterministic in nature. Now, the other processes are known as stochastic in nature or probabilistic in nature, where we cannot 100% guarantee the outcome of the process in spite of rigorous planning. For example, suppose I want to catch a flight for Hyderabad to attend a meeting at 5 p.m. and considering all the local traffic conditions and flight delay and the local traffic conditions at Hyderabad also, all the overheads considering, if I consider and I take a margin of extra 2 hours probably, then also it may happen that I may miss my flight or I may miss the target time to reach to the destination. And the reason could be manifold. The reason could be either your flight may be, cancelled because of some technical fault, or it has been excessively delayed, which you could not postulate it. Or the other way out, the other could be like in the local traffic conditions, you may have to deviate from the normal path and have to take the alternate path to reach to the airport because of some construction work that is going on, and which these scenarios you could not postulate basically, and hence you may miss the target in spite of rigorous planning. So what I mean to say is all the nature of law, all the law of nature are basically deterministic in nature, and all the systems which are made by the human are probabilistic or stochastic in nature because the outcome cannot be 100% guaranteed. And even there is the concept of the human reliability because of this stochastic behavior. So definitely the creation of this human, what about all the systems we are talking about, definitely those will have some kind of randomness in their system, and hence there should be separate or different mathematical models or models to uh, capture the stochastic behavior of such kind of systems, for which PetriNet it is a very good model, and we will see how what are the basic building blocks of the PetriNets, what is the working mechanism of the PetriNets, because we are going to utilize this mathematical formalism for quantification of the reliability. Then we will see some of the properties of the Petri nets and what are their analysis techniques. And after that, I will propose the reliability prediction framework. There, I'll be discussing all the phases and of that particular framework to quantify the reliability, and I'll be discussing all the activities which needs to be performed in each of the phases. And I'll be also taking a real case study in which I'll be trying to demonstrate all this framework so that it can be easily used by the participants, or you can easily understand, like, once you will be able to understand applying that framework on a real case study, then we can conclude our session. So if we talk about the mathematical representation of the reliability, so suppose x be a random variable. Once I say the random, it means it's a probabilistic in nature. You are not 100% sure about the outcome of the process. So let x be the random variable which represent the time to failure of a component. So the reliability, it means up to x time, it should not be fail. If I'm taking a target time t, it should always be x must always be greater than t. Then only I can say it is 100% reliable. So the reliability of the component at time t is given by Rxt. As I said, it's a function of time, and x is a random variable because it represents the operating conditions as well, because it is representing the failure of the component. So that can be given by the probability that the value of x must always be greater than t, because t is a target time and it should not fail before time. So from the mathematical, but from the probability theory, we can write it is equal to 1 minus p and x is less than is equal to t. So what does this p x is less than is equal to t mean? It represents the probability that my component has failed before the target time t. So it is a failure probability. It means it has failed. So we can write is equal to 1 minus fxt, and f represents a failure probability. It is also a function of time. So we can conclude that reliability is equal to 1 minus failure probability, or failure probability we can term as unreliability also. So the reliability plus unreliability will always be is equal to 1. Okay. Sorry. So now let us have a look on some of the traditional methods that are being used for the reliability quantification. So the one is the reliability block diagram. It's a very prominent model, and it is a series and parallel reliability block diagram which represents the logical structure of a system. And with the regard, to how the reliability of its components affect the system reliability. For example, if I'm taking a system, a laptop, for example. Now, laptop contains so many components like mouse, keyboard, power button, screen. These are the different components, ICs, and those components are arranged in series and parallel, logic, depending on the system design. So now the how we can calculate the then reliability of this particular system. You can assign the reliability of the basic components. Now, what could be the basic component? For example, in the case of laptop, you have to keep on deducing. For example, if I say the keyboard is not working, then you'll have to try to find out a root cause. Probably ICs are not working, and you can assign the reliability of these basic components from the database. There is an open catalog which so several catalogs are available in the online, like military handbook, or if even you are dealing with the mechanical components, the failure of mechanical components, failure rates or the reliability values are given in those catalogs, which you can use. And if the components are arranged in series, you have to calculate the reliability of the overall system by using the series reliability formula. And if they are arranged in parallel, you have to calculate by the parallel reliability formula. You can calculate the overall system reliability by using the parallel reliability formula. For example, if in a system you do have only two components, let it be the C1 and C2, and having the reliabilities R1 and R2 respectively, then the reliability of the overall system is given by R1 into R2, which is a series reliability formula. So in this way, we can keep on solving till we reach to the system level. And the other important modeling technique for computation of the reliability are known as reliability graphs. And the reliability graph model, if you talk about the basic constructs or the basic building blocks, it consists of a set of nodes and edges. It contains directed edges, basically. And nodes are used to model the link between two components, where R is used to model the components in the system. So, if you are able to see this figure, the left figure represents the reliability graph. And where A, B, C, D, these are the vertex, and edges are named as V1, V2, V3, V4, V5. And as I said, these edges represent the real components, and the vertex basically represents the connectors between those components. So this reliability graph can be equivalently transformed into the reliability block diagram, which is, you can see the representation of reliability block diagram. The equivalent reliability block diagram of this reliability graph is shown in the right side, right figure, where all the B's has been replaced by the components 1, 2, 3, 4, 5, and all the vertex have been represented by the connectors. And now you can solve, for example, 1 and 4 component are in series. You can assign the reliability of 1 and 4. Then you can use the series reliability formula. You can assign the reliability of component 2 and 5. And you can apply the, again, series reliability formula. Now all these three will be in parallel, so you can apply the parallel reliability formula to compute the overall reliability of the system. Now, coming to next, a very prominent model specifically being used in the safety critical systems are known as fault trees, which are being used in railways, in nuclear domain, in medical domain. And fault trees basically represent all the sequences of the individual component failures, which can cause the system failure. And it is in a tree-like structure. For example, suppose considering the same example, laptop is not working. Now I can deduce the root causes why laptop is not working. So the root causes could be either it is power failure, it could be the mechanical failure, it could be the electronic failure. Now if I want to deduce the power failure, there could be various events. Probably the socket at the source side is not working, or power is not coming at all, or there could be a break in the wire which is connecting to the laptop, or there is a loose connector in the laptop side even. So these could be multiple reasons or basic causes of the power failure, which can be arranged in AND or OR logic depending on your system. Similarly, if I consider about the electronic failure, that may be that may include the failure of ICs, the failure of resistors, the capacitors, like this. In the case of mechanical failure, you can, like, power button is failed to press, or the screen is broken, or the wheel of the mouse is broken, and so on. And these can be connected. So ultimate, the basic game is we have to keep on deducing the root causes till we really reach to the basic component or the basic cause. And then we can assign the probability of failure of the basic cause, and we can find out the top level probability. For example, if I say, I'm taking a simple example, like I'm having the observation that human is not able to see. So this is my observation. So this will be my root of that tree, of the fault tree. Now, what could be the cause? I'm taking two very basic causes. If his left eye is all not working and his right eye is not working. So both the event should be in AND logic. So it means, and suppose the probability of the failure of the left eye is P1 and that of right eye is P2, and because they are arranged in the AND logic, so that human is not working, human is not able to see, that probability will be multiplied P1 into P2. And as I said, it is the unreliability. So reliability, to compute the reliability, we can negate it by 1. We can subtract it by 1. So 1 minus P1 into P2 will be the total reliability of that particular human being. Now, the events can be arranged in OR logic also. So suppose if there are the two root causes having the probabilities of failure P1 and P2 and are arranged in the OR logic, then the top level failure probability will be P1 plus P2. If they are arranged in the OR logic, we'll have to add the probabilities, and then again the reliability will be equal to 1 minus brackets in bracket P1 plus P2. So basically the starting point is a definition of a single well-defined undesirable event, which is a root of the tree. And in the study of the reliability, this undesirable event is known as the failure probability or the failure event. Now, the models, we have seen some of the prominent models that are being used for computing the reliability. But the model that we have seen so far, they are very fast, but they assume the stochastic independence between the system components. In the sense, we assume like each component is failing from its own. While if you see the dynamics, probably one component may fail from the other component as well. The root cause may be for the other component, may be the root cause for the failure of one component. And this stochastic dependence we have to really accommodate. And the models that we have looked so far are incapable to model this stochastic dependence between these system components. So here we have to make the assumption in these models, traditional models, that the failure or the repair of a component is not affected by the other components. So if you want to model more complicated interactions between the components, we have to use some other kind of models and are known as the stochastic models. And the type of the stochastic models are many that include Markov chain, or the patrinets, the state transitions. There we can model the dependencies among the system components. So if you look into the Markov models, these are the most powerful tools for the reliability and safety analysis because they provide the modeling capability for all sort of dependencies, whether they are arranged in the non-series parallel logic or having different kind of redundancies, diversities, or different configuration. And it has a capability to depict the stochastic process. So if you look into the modeling construct or the basic building blocks of the Markov chain, it contains mainly two things. One is the states, one is the set of states. You can have several states and the transition probability between those states. For example, if I take the human being, I can have the several states that includes eating, talking, walking, sleeping, running, moving, and so on. And I can transit from one state to another state. So definitely, and the probability, transiting, there should be some probability associated with that transition, and that will depend on my statistical history. That can depend. So, so there is a transition rate that is very important. Transition rate means how many number of times per unit time I am transiting from one state to another. So, for example, if there is a system having only two states and which are I and j, and let qij be the transition rate from state I to state j, then we can define the transition rate from I to I, or the self transition rate will be equal to minus sum of all the rest of the transition rates from that particular state. Right? So this is the so what I mean to conclude in the stochastic modeling technique. We try to decompose any system into various states rather than into their constituent components. And if we can find some way out to compute the probability of the system being in those states, then we can sum up the probabilities of all the successive states that will give the probability, that will give the success probability or the reliability. The other way out, we can find the probability of the failure states because the failure states are generally very less, and we can sum up the probabilities of all the failure states, and then we can subtract by one to compute the reliability. So in this way, we can compute the reliability of the overall system. Now I'm discussing some of the, defining some of the terminologies. So one is a Q. It's a matrix known as generator matrix, which is n into n or n cross n generator matrix, or we can say it is a transition matrix or transition rate matrix, where we can write the columns and rows with the number of states, with all the states, and we can fill in the elements of the matrix with the transition rate from one state to rest of the states. We can map that. We will see when we will consider the case study. Now, after Marco 15 coming to the battery nets, which on which we had discussed during our start of the talk. So, as I said, this concept was introduced in 1960s by C.A. Petrie, who was a PhD research scholar, and it is a very good graphical as well as a mathematical. And why graphical too? Because we can depict the behavior of the system using this battery, and we can see how at the runtime or when it will be converted into the product, how your system will work. And that helps in a multiple ways all the stakeholders, starting from, for example, I'm a businessman, and I want to export some project. I want to outsource some project to any development agency. So I have written the requirement specification of that particular system. And that development agency, although they have studied the requirements specification very sincerely, but then also there are many scenarios which they are not able to understand, and for which the peer discussions are required. So what they can do, they can model in the terms of they can model all the functional requirements in the factory net, and they can demonstrate so that I can see whether all the function requirements have been captured and the working principle of the system is exactly meeting to my specification. And so if it is not, I can take the design decision thereafter for the preventive actions. And it is a mathematical tool as well, because we can use mathematical knowledge and to know more and more insights about the system. So, insights in the sense we can identify various dependability attributes that include reliability, safety, security, and so on. So, it is a very good communication means between theoreticians and practitioners. And if you look into the history of the battery net, as I said, the concept was introduced in 1962 in his PhD dissertation of C.A. Petrie. And after that, his thesis was read by various researchers, and MIT USA was having a thought whether this model can be utilized to model the concurrent systems or parallel systems, because in 1970 they were striving, there was an era to work on the parallel systems, and they want to see whether some model can be used to model such kind of systems. So with this objective in 1970, MIT USA conducted a conference on concurrent system and parallel computation. And the conclusions were very fruitful, and they was then eager to know the related methods that can be used or whether the model can be strengthened, the modeling capabilities can be strengthened so that it can be used for the purpose of industrial applications. And with this objective, they again decided to meet in 1975, where MIT USA conducted a conference on factory nets and related methods. And after that, it starts gaining popularity in the industries also. So industries used to recruit the persons and they used to impart the training to those recruitees, and for which they have to stay at least 6 months of training or three months of training, depending what is the nature of the work that they want to take from this. And so to save this industry time and because the demand was more, Germany started a course on general net theory of processes and systems in 1979. And then the people from the different domains were also trying to look into whether the battery nets have a capability to model their specific kind of systems. And with this objective, France conducted a first European workshop on applications and theory of battery nets in 1980. And then the researchers were coming out with the different flavors of battery nets. For example, if you want to work on the real-time systems, definitely timing information plays a very important role too for the performability. And so a different flavor of battery net known as timed battery net was introduced. And the first international workshop on the timed battery nets was conducted by Italy in 1985. So, I mean, this is not an exhaustive list of the milestone of the battery net, but it gives a motivation about the importance of this modeling construct and how it has gained a popularity because of the milestones. And if you look into the battery net applications, basically it is able to cater all kind of applications. Now, let us see the basic building blocks of the battery nets and what is the working mechanism of battery nets with the help of very small example. Then we will take a real case study so that you will be able to appreciate the modeling of the battery nets. So, but first I'm explaining this working mechanism on a very small chemical reaction which you might have studied in the class 10th, like 2 hydrogen plus oxygen, it gives water. Okay. Now I want to model this chemical reaction. So first let us understand the basic building blocks and then I will explain the working mechanism to know why these basic building blocks are required. So in this figure, if you are able to see the big circles, there are 3 big circles. One is to represent hydrogen, one is to represent oxygen, and one is to represent water. And this is known as place. This big circle is known as place. So there are 3 places in this battery net figure. Okay. One is representing hydrogen, one is representing oxygen, and one is representing water. Now, there is a rectangular bar in this figure, which is known as transition. So there is a one transition in this figure, and the places are connected with the transitions, and transitions can be connected with the places. But there can be no direct-to-direct connection between the places and between the transitions. and the connection is known as arc. So you can see in this figure the hydrogen place is connecting with transition T, oxygen place is connecting with transition T, and transition T is connecting with water place. Next, you are able to see there is a numeric number that is assigned on each arc. These numeric numbers are known as weight of the arc. You will see the significance of this weight later on, but here if you see in the figure, the weight of the arc that is connecting hydrogen place and transition T is 2, oxygen place and transition T is 1. I have not kept any weight, so by default it is treated as 1. So if or you can keep numeric number 1 also. And the weight of the transition that is connecting transition, sorry, the weight of the arc that is connecting transition T and water place is 2. Now there is a concept of input arc and output arc. So the arc from which entity, from the entity where it is emerging, for that entity the arc are known as output arc. And the arc where it is terminating, for that entity the arc are known as input arc. So for example, in this figure, the hydrogen place contains one output arc, the oxygen place contains one output arc, the transition T contains two input arc that are coming from hydrogen place and water place, and one output arc that is connecting with water place. Similarly, the water place contains one input arc that is coming from transition. Now, there is the concept of tokens. You can see. Okay, one thing more before that. So the places which are connecting with the input arc and output arc are known as input and output places respectively. And similarly, we can define the input and output transitions for the places. Now you can see there are some embedded circles inside the place, hydrogen and oxygen, and these embedded circles are known as tokens. So for example, this hydrogen contains 2 tokens. So hydrogen place contains 2 tokens, and I'm representing these tokens to represent the number of atoms. So hydrogen contains 2 atoms, so I'm representing it by the tokens. Similarly, oxygen contains 2 atoms, so I'm representing by 2 tokens. Now, this distribution of the tokens among the places are known as states, or represent the state of the system. So, for example, in this figure, the distribution is 2, 2, 0, because hydrogen place contains 2 tokens, oxygen contains 2 tokens, water contains 0 token. So 2, 2, 0 is the state of this particular system. And this figure represents the left side of this reaction, that is 2H2 plus O. So it is a so it is the initial state of the system. Now it has to convert it into the water. So it means the state needs to be changed. And one thing more, the states can also be known as marking. So marking or states are same. Now the states can be changed only if at least one transition in the battery net is in enabled state. I repeat, listen carefully. The state of the system can be changed only if any transition is in enabled state. For example, in this figure, there is only one transition. So if I want to change the transition, if I want to change the state, the transition must be in enabled state. But what is the criteria of the enablement of the transition? The criteria is all the input places of that transition must contain sufficient number of tokens. So it means, what are the input places of this transition? Hydrogen and water. So these two places must contain sufficient number of tokens. And who will decide the sufficiency criteria of the token? Here the role of weight of the arc comes into the picture. So the sufficiency of the token will be governed by the weight of the respective arc. For example, the weight of the arc which is connecting hydrogen place and transition T is 2. So if for T is enabled, the hydrogen place must contain at least 2 number of tokens. Similarly, the weight of the arc which is connecting oxygen place and transition T is 1. So oxygen place must contain at least 1 number of tokens. So in total, the hydrogen place must contain 2 tokens and oxygen place must contain 1 token. So now T is in enabled condition. So when it is enabled condition, then it fires, and after fires, the movement of the token happens from input places to output places. So the token starts removing from input places and it starts depositing in output places. Now, how many tokens will be removed from the input places and how many will be deposited to the output places? This also will be governed by the weight of the respective arc. And here the weight of the arc which is connecting the hydrogen place is 2. So the 2 tokens will be moved out from hydrogen, and weight of the arc which is connecting oxygen place is 1. So 1 token will move out from this oxygen place. So total, and now how will be deposited into the output place? Again, it will be governed by the weight of the output arc of this transition, which is 2. So 2 tokens will be deposited in the water place. So one interesting conclusion that can be drawn here is, although 3 tokens are removed, if I'm summing up the number of tokens from all the input places, but only 2 tokens are deposited in the output place. So what I mean to conclude is the removal and deposition of the tokens from the input and output places respectively will be totally depend on the weight of the input or output respective arcs. Okay. So the next, after firing, what will happen? The 2 tokens will be deposited, has been removed from hydrogen, and 1 token has been removed from oxygen, and 2 has been removed to the water place. And now we can see the enabling condition of the transition too. So you can see what was the enabling condition, that all the input places must contain sufficient number of tokens. So it means hydrogen place must contain 2 tokens, which is not containing. Although the oxygen is containing 1 token, but it is here, it will be AND logic, not OR logic. So transition T is not in enabled state. And hence, this now the state will be final state, no movement of the token will occur because no transition is in enabled state. And now the distribution of the token has been changed to 0, 1, 2 because hydrogen contains now 0 tokens, oxygen contains 1 token, and water contains 2 tokens. So 0, 1, 2. So now it represents a very interesting point. Like it is helping out. It is helping us out in identifying the number of states that are possible of that particular system, right? So here only two number of states, and if I'm able to find out the number of states, I can draw the reachability graph. Reachability graph means what all the states that are possible throughout the operational time of the system that can be reached. So one state is this 220, and after transition T, it has reached 0, 1, 2, and this is the final state. So the reachability graph can be drawn. So this was the working principle of the Petri nets. Now analysis techniques. Coming to analysis techniques, you can see the success of any model depends on two factors. One is it should have the modeling capability. Second one, it should be able to derive some of the insights of the system, take some decision. And we have already seen like the modeling power of the Petri net and decision power. We will see like when we will be discussing in a case study how it can be used for the quantification. Now coming to the Markov chain again, just I want to show the mathematical representation of this Markov chain. So suppose there are only two states, S1 and S2, and definitely the transition can happen from S1 to S2 or S2 to S1. Then the current state, in what Markov property says, the next state of the system will only depend on the current state of the system and not on the previous state of the system. And that is what it is written in this mathematical form. So suppose there are a sequence of random variables x1, x2, x3 with a Markov property. Then what Markov property says that the probability that the value of this random variable that it is in state x will only be depend what was its state at n time. So the probability that my system at n plus 1 time is at, it will depend only on the nth time and not on the previous states, right? So we can write it down is equal to p xn plus 1 is equal to x, given xn is equal to xn. Now this slide is just a random slide just to introduce the reachability graph, how we can represent the reachability graph. So if you are able to see the left hand side figure, it is a reachability graph where these are markings 100. It means I have considered some random Petri net figure which contains 7 places and having the token distribution like this. One in first place 1, second place 0, third place 0, fourth place 1, like this. And after transition T1, it is changing to this distribution, for example M2. Similarly, after M2, it is changing to M4, and like this. It's a random example, and we can easily convert it into the Markov chain because M1 is what? It is just a marking, so it is a state. And in the Markov representation, we represent the state by circle. So these 1, 2, 3, 4 are representing the states M1 to M2, M3, M4, and these lambdas are known as transition rates between these states. Now let us introduce the reliability prediction framework. What are the various phases for computing the reliability prediction or for computing the reliability? And the phases include are the Patrinet model creation. First, we have to create the model of the Patrinet. Then we have to convert it into the Markov chain. And then the third phase is we'll have to use the mathematical knowledge to compute the reliability. We have already seen how we can create the Patrinet model while we were discussing the example of water reaction. And we have also seen how we can convert it into the Markov chain by first converting the Patrinet model into the reachability graph, and thereafter we can transform it into the Markov chain. And phase 3 we will discuss. So although all these phases we will be executing on the real case study which we will be taking, but before going through the real case study, let us create some of the foundation, mathematical foundation that we will be using in our prediction framework. So suppose IIT be a probability that a component is in a state I at time t, where I could be failure states or behavioral states. Behavioral states, for example, when I was giving the example of human being, like he can have several states like running, sleeping, walking, talking. These all are behavioral states. And if I say it is meeting accident, these are all the, so it is a failure state. Right? So it can have the failure state as well as behavioral states, and as t goes to infinity, these probabilities converge to the stationary distribution. So what I mean to say is, whenever you will take a longer time, or any system takes a longer time to settle down, and the more complex the system is, the more time will be taken to settle down for a stationary distribution. And for example, suppose you fill a water in a glass, and you will see like at the initial time, the water will be zigzagging. And after some time, you will see like water will settle down, and now you just replace this glass with a very huge container, for example at the size of the room, and you just fill in the water and just lift it up and put it down. You will visualize, or you can see, it will take a larger, huge, significantly larger time to settle down as compared to it was taken by the glass in case of glass. So what I mean to conclude, if your system is more complex, it will take more time to settle down. And these are the convergence probability, so it will converge to some stationary distribution. So pi estimator is the convergence probability, and which can be computed by the following equations. Now these two equations are very important. I'm discussing those equations conceptually. So the first equation, it is very simple. It simply says the sum of the probabilities of all the states a system is in at a time is always visible to 1 because of the total probability law. So if I have a 10 states S1, S2 up to S10, then and all is having different probabilities at a time t, so S1 plus S2 plus up to Sn is equal to 1 always. Now the next is this equation is very important, and let me make you understand conceptually. Now take the same example of the huge container where you are filling with water. So you can see at the initial point of time, the water will be very zigzagging, and suppose the initial state is S1. And after suppose delta t time, it is propagating towards settling process. And suppose it have reached to S2 state, then S2 will be depending on S1 and the transition probability from S1 to S2. So how we can write S2 is equal to S1 into transition probability from S1 to S2. Similarly, further after delta t time, from S2, it reaches, for example, S3 state, more settling, propagating towards more settling process, then S3 will be equal to S2 into the transition probability from S2 to S3. And the process keeps on continuing. And suppose at one point, example, at Sn, the process has been completely settled down. Then what will happen after delta t time? Sn plus 1 state will be equal to same, that is Sn. But the equation remain hold same. That is Sn plus 1 is equal to Sn into transition probability from Sn to Sn plus 1. So this is what this equation says. So this is the stationary probability is equal to, which is going to remain same, and into the transition probability matrix, because we are dealing with multiple states. So it will be both the transition probability matrix. We'll see how we can calculate these while we will be considering the case study. Now let us take a case study of the communication module. And the protocol is very simple. Suppose you want to call a friend. So what you will do? You will just pick your mobile, you will dial the number, you will wait for the ring to go, and once your friend will lift your phone, you will say hello, and you will wait for the acknowledgement. And in case you are not getting any acknowledgement, you will feel like, okay, the message has not been reached, hello to your friend, and again you will say hello. And you will keep on doing till you are not getting response. But up to how much time you will keep on doing? For example, if certain time, probably 10 seconds or 20 seconds, if you are not getting any response, you will ensure, or you will come to know that your connection has been lost, and you will cut the phone and retry. And what you will do that in the retry, again you will you will cut the phone, and again you will dial the number. So the same philosophy has been adopted in this communication module. So suppose there is an embedded unit which is capturing the data from the field sensors, and it is processing the data and it is sending to some display unit. So whenever any embedded unit sends a new packet, the value of the count is set to 1. I have kept one variable known as count just to keep a trace how many packets have been sent. And after sending, embedded unit will wait for the acknowledgement for certain period of time, for example T1 after sending packet. And if embedded unit receives acknowledgement before T1 time, the packet send is successful, and the semaphore variable is changed to its complement. So if count is less than n, but up to I mean up to I'll have to keep n number of times trials. But then also if I'm not getting acknowledgement, the embedded unit retransmits the packet and set the count variable and increase the count variables. Otherwise, the embedded unit terminates the send process unsuccessfully, where the semaphore variable will not change at all. And after T1 elapsed, after the last data sentence, we have to destroy the semaphore. And this is the communication protocol, and let us see how we can model the battery net. So this is the battery net model of this communication module, and let me explain what are the places and what are the transitions of this protocol. So you can see, interestingly, all the weight of all the arc is 1 because I have not put any arc. So it all depends on the context of your system that you are dealing with. So the PSRDY0, it represents like embedded unit is ready to send the packet with semaphore variable 0. And I have kept one more place to represent like embedded unit is getting a request from display unit to send the data. So at the initial time, I have kept the tokens at both the places. Then TS0, it represents that embedded unit sends the packet with sequence number 0, and it set the retry count k is equal to 1 by firing this transition. Then PSW0, it represents the place which is waiting for the acknowledgement with sequence number 0, because every packet has a sequence number, so it was waiting for the sequence number 0. And then TSW0 represents like embedded unit detects the timeout of the acknowledgement. And if it detects the timeout of the acknowledgement, so acknowledgement timeout is will be considered when the token will be deposited in PT0 and 0, and then after that it will resend the packet. It have to send the packet again. So it is the transition TS0K, which is with the sequence number 0, and this transition is fired only when K is less than N, and we have to subsequently increase the value of K. And this process keeps on going till it is less than N. And once it is reached, for example, the data packet has of 0 sequence number is sent, which is represented by the place PS0S. Then it is a communication line TCOM1, which represents like data display unit sends the acknowledgement to the embedded unit with sequence number 0. And here the acknowledgement number will be received, which is represented by PR1R. And then because the acknowledgement has been received, it will pull the tokens from both these places and set it to, again, it will initialize the system for sending another packet. But one thing we have to consider, if I'm not able to get the acknowledgement up to some period of time, what will happen? For that, it will go to this trigger, the TS0 ACK suck, where we will decide like process of data send is terminated without success after n trials. And it will fire only after when k is greater than n. And then the token will be deposited in PDSAU, which present like data send is unsuccessful and is reported to the operator. And now, interestingly, you can see this is the half, the left half of this figure is exactly mirror image of the right half. This is why, because we have taken the redundant embedded units and display units for the improved reliability. And we are sending the data packets from the alternate embedded units, which facilitates the online testing also. So now online testing is very important. Like when suppose I have kept one component for redundancy, and I'm using one component, and if I find some failure in that particular component, I will switch over to the second component. But what will happen if I don't, if that another component was also in fail condition when I had put in the operation? So for what would I do? I can have two provisions. Either I have to check the redundant component periodically, probably after 1 month or 2 months, depending on the frequency that will be decided by the system analyst. Or, but there is one problem in that. So, in fact, there are the two problems. One is the overhead of the testing, because every time you have to use the manpower, and you have to record the data for testing those components. The second problem is, suppose the testing interval is 1 month, and I have tested today the redundant component, and suppose tomorrow the main component fails. Tomorrow or after 10 days, the redundant component has failed. But I have not tested because my testing frequency is 1 month. And after 15 days, my main component also fails. Then I wanted to, use the second component or the redundant component. What will happen? That was also in fail condition. So I will be stuck. And hence, the online testability is an important feature where all the time both the redundant component as well as the main components are being used. And hence, we can ensure like anytime when one component fails, the other component will be able to take up. Now let us see what next to be done. So the next is we have to assign the model parameter. So this is the model, and because we are dealing with a real-time system, we'll have to assign the parameters of delay, these transition delays. And these transition delays are derived from the statistical history of the similar kind of projects, or from the system analyst There are various sources which basically derive this model parameter, and we may have to use the artificial intelligence or data science techniques to derive such kind of delays from past similar kind of projects that are already in operational phase, or from the system analysis, from the system specifications, and how to club them and to come out with effective data. And then we can use the various tools which can run the PatriNet model. There are various tools available like TimeNet, Petri, CPN. So I have used the TimeNet, and which can give the throughput of each of the transition. Throughput is nothing but it is the firing rate, or the number of firings per unit time of that particular transition. So for all the transitions, I have got a throughput. So now we can create the reachability graph. You can see like how the tokens, if you can go back, earlier it was having a token in this place and in this place. So this transition will be enabled TS0, and after firing of this transition, these tokens will be moved out to both of the output places, right? So the same thing is done. So M0 means earlier there was a token in other place, two places, and which has been removed in the next marking and start and deposited in their output places like this. So till we reach, till we get all the states, and these states are tangible states. So states basically are of two types. One is the vanishing state and one is the tangible state. So vanishing states are those states where when we put the transition delay 0, it means those transitions are known as immediate transition. It does not have any delay in firing. And in the tangible, uh, when we put some delay, so it will be a tangible marking. And for easiness, for ease of representation, we have just mapped all these transition rates with lambda 1 to lambda 12. There was the 12 transition just for the representation purpose, that's it. And then we can draw the reachability graph. You can see from this is M0 marking. So this is the first state. Then after transition TS0 firing, it reaches a one state and so on. We can keep on reducing till we reach to the entire state space. So it's a reachability graph creation, and we can create a Markov chain from this that we have already seen. So each state we are representing by these circles in the Markov chain, because this circle represents the states, and the throughput of every transition, or it's a firing rate, or it's a transition rates, these are represented by lambdas, all the lambdas. Now it is a Markov chain creation. Now we have to derive the transition rate matrix, or the generator matrix that we have discussed during the initial time when we were discussing the Markov chain. So I'm just going back to that particular slide so that you'll be able to appreciate this slide. Yeah, this is what. So this is the Q is a generator matrix or transition rate matrix, where we have to mention all the states, and we'll have to fill in the elements with the state uh, transitions rate. And this equation is very important, which we will be using in deriving this matrix to fill the diagonal values. So it is just the self transition rate will be equal to minus summation of the transition rate from that particular state to rest of the states, and this equation will be using in deriving this transition rate matrix. So here we have used, this is all the states M0 to M9 in the rows and columns, and we have to fill in the elements. So you can see from the Markov chain, from M0 it is going to M1 with lambda 1 transition rate. So from M0 it is going to M1. And then the self transition, as I just showed you this that equation, it is minus summation of all the transition rates. So it is minus lambda 1. Similarly, from M1 it can transit to M4 or M2 with the lambda 11 and lambda 3. So M1 is transiting to M4 with lambda 11 and M2 with lambda 3. And hence that from M1 to M1 transition will be equal to minus summation of lambda 3 and lambda 11. And in this way we can fill in all the elements of the transition rate matrix. Now next we have to derive the transition probability, and the concept is very simple. If I want to find out the probability, transition probability from state I to j, it will be equal to the transition rate from I to j, and we have to normalize this transition rate. So we have to divide by sum of all the transition rate from I to k, where k should not be I. And this holds when j is not equal to I, otherwise it will be 0. So you can see this is the transition probability matrix where all the diagonal values are 0 and rest of the values are computed by this first equation. And then just recall those two important equations which I was discussing when I was taking the water in the big container. So this is these are the two equations, and one is nothing but it is sum of all the state transitions. So M0 plus M1 plus M2 up to M9 is equal to 1. And this is, second is the stationary equation, which is written here like this, M0. So these are the stationary states, which is equal to same into the transition probability matrix. And you can solve these two equations and you can find out the state transition probability of every state. And interestingly, you can see if you go back, there are the two states where the packet sent was unsuccessful. One is M3 and one is M8, because here the unsuccessful transition got fired. So what you can do, either you add all the state probabilities other than M3 and M8, that will give you the reliability quantification, or the other way out, you can sum up the reliability of state probabilities of M3 and M8, and you can subtract it by 1. This is the reliability of the communication module. So that's all I wanted to share basically, and if you look if you recall, basically the whole idea is you can model any system using the state space models and then try to find out the probability of the failure or the probability of a system being in failure states or being in success states. And if you sum up all the success is probability, that will give you the quantification of the reliability. So, but definitely this patchnet modeling, it really requires the expertise. And but the benefits that overweighs the failure of effort, and especially if you are dealing with the safety critical system. So that's all I wanted to convey to you. In case of any questions, I'll be happy to answer.
If anyone wants to ask question, they can ask. Okay, so I call now Aditya Shastri for vote of thanks.
Good afternoon, ma'am. Am I audible?
Yes.
Okay.
Yeah, so
So, good
one
afternoon.
question is there,
Oh.
Aditya, you can ask
Oh,
in chat box. Sir, we
okay.
are beginner in critical system theory, so how we start?
Yeah, we can start definitely from the textbook, because if you are beginner, definitely you should not start with the papers, because papers are generally advanced in nature and it represents the current state of the art that is going on. So definitely you can refer, the textbook, and if you want to, for example, the basic textbook of reliability engineering for safety critical systems is by E. Balaguruswamy. It is a very basic, book from where you can get a lot of fundamentals and mathematical concepts. And once you can build your mathematical concepts, you can go for the more advanced textbooks, and you can take the Google help, and then you can start surveying the papers and all, what are the current state of art that is going on. So this is the way basically any new technology, when we want to learn, we have to just first try to make our fundamentals strong. Okay.
Okay, and sir, how we understand maths calculation?
See, it requires your mathematical foundation, because like when if you see like even any good paper, especially any like IEEE transactions or ACM transactions, mostly they talk in the terms of mathematics. So definitely you'll have to be good into the mathematics. You have to have a very strong mathematical background, or if you don't have, definitely you'll have to do that. For example, like algebra or matrices, matrix theory, theorems, devising lemmas. So all those, it requires the hard work, and you'll have to, create your basic foundation, so that you should be able to come to a level where you can understand the good papers, basically. Because most of the time, the people are not able to understand the papers also. They are so mathematical that you cannot understand until your mathematical concepts are not strong. So definitely you'll have to start with the basics to improve your mathematical background. So there is no shortcut, basically.
Yeah, okay, thank you, sir. Aditya, over to you.
Okay, ma'am. So, good afternoon, everyone. I'm really gratified for giving me a chance to deliver the vote of thanks to such a honorable audience. It was a really great time with you, and I assume that you also have got lot from this meeting. I am thankful to Dr. Lalit sir for truly making this session full of knowledge for us, and Your deep and intellectual way of imparting the knowledge has added a glory to this session. We have got a lot of information regarding the topic reliability prediction for critical system. It is started very well, and then will be go to the case studies and go through the mathematical expressions and examples. So I must mention our deep sense of appreciation for demonstrating excellent coverage over the in-depth learning about critical theory prediction and sharing a lot of things. So we have no words to offer gratitude for your valuable presence in this session. Your deep insight into these topics and revealing some interesting facts about these topics will definitely motivated us to gain more knowledge and work hard in our respective fields. So once again, I would like to thank Dr. Lalit Singh sir for taking out time from his busy schedule and enlightening us with the knowledge. Over to Mukti ma'am. Thanks.
Okay, thank you, Aditya.
Thank you. Thanks.
Thank you, Lalit sir, for your knowledgeable and informative session. Thank you very much, sir.